In Chapter 18, we begin to look at a cost-volume-profit analysis. And what this type of analysis does is it takes what we understand about the calculation of a profit. If you'll remember, profit equals revenues minus expenses. And we look at if we change any of the variables that go into your profit calculation, how does that affect your end result or your end profit? So if we change any of the variables that make up our revenue, or if we change any of our expense variables, what does that do to our bottom line? And so this is a cost, volume, profit analysis, meaning we're going to be analyzing what happens if you change costs, if you change the volume of your products being sold, what does that do to our profit? But before we can get into a CVP analysis, we first need to get a deeper understanding of cost behavior. So what we're going to be spending a lot of our time on is understanding the total cost of making a particular product. Total cost is made up of two types of costs. That's our fixed costs and our variable costs. Most products have both fixed and variable portions, so we need to understand the behavior of the fixed costs and of the variable costs that make up our product to be able to perform a CVP analysis. So first we need to define a little bit more about what is a fixed versus a variable cost and how does that affect our profit. So we're going to be getting an understanding of how much does income increase if we install a new machine, and therefore we're reducing our labor costs. So that's a question of if we change our labor expenses, what is that going to do to our bottom line? And we'll analyze, are we getting rid of variable costs? Are we adding fixed costs? And if so, what does that do to our profit? Another example of what we're answering with a CVP analysis is what is the change in income or in profit if selling prices decline and sales volume increases? So in this case, we're looking at the revenue part of a CVP analysis because we're saying if sale price declines and sales volume increases, are we going to see an increase or a decrease in our total revenue? And that all is determined by dropping our prices. If we have a small drop in our price, is it going to increase our sales volume enough to make up for that drop in the price? Because we'll be selling more, and therefore each unit is going to be sold for less. But does that mean we'll make more revenue overall because of the higher volume? So these are the type of questions we're answering with a CVP analysis. Remember, cost, volume, profit, CVP analysis. So how will our income change if we change the sales mix of our products or services? We'll look into these type questions as we get to the very end of this chapter. But in this case, we would be looking at a company that makes two products. Let's make it easy, product A and product B. And when we talk about the sales mix, we're talking about of our total sales, how many of those sales are product A versus product B. So let's say 60% of our sales are A, 40% of our sales are product B. That's what we're talking about, the sales mix. So companies can change around the sales mix to help improve their profit, and we'll look at that as we move on. Then we'll look at what we call a break-even analysis. We'll use the break-even analysis to help us understand what volume we need to sell to break even. If you break even, this is a point when you're making a profit of 0. Or in other words, you're not making money, you're not losing money, therefore you're breaking even. Once we understand the break-even analysis and how to calculate the break-even analysis, we can expand that. So rather than saying that we want a profit of 0 or that break-even, we want a profit of some kind of target income. Once we learn the break-even formula, we can expand it to calculate various target incomes and what volume is necessary to meet a particular income level. So these are all the different things that we can answer once we understand a cost, volume, profit analysis. But before we do that, we first need to get a better understanding of our costs. We're going to look at fixed costs, variable costs, and then the two of those together make up total costs. So let's look up here at this top graph. Then if we look here at the bottom graph, we're going to expand on our explanation. But what I want to make sure that you understand is that these graphs are graphs of our costs. but we're looking at our costs differently. This top graph is our total costs. So these are the total costs if you sum up the costs of all the products that we make. This is our total cost graph. On the other hand, down here you're seeing your total costs on a per unit basis. And we'll talk about these as we move forward. But just so you make sure you understand, this top graph, we're talking about total costs. The bottom graph, we're looking at costs on a per unit basis. So let's define what's going on here. The first thing that I want to note is our fixed cost line. Okay, fixed costs here are shown as a horizontal line. And let's go ahead and define fixed costs. Fixed costs are a type of cost that does not vary in total dependent on the quantity or the volume of products that you make. So an example of a fixed cost would be rent. If you rent a building for $100,000 a year, it doesn't matter if you do anything in that building. So you could make 0 products and you still have to pay that rent. Or you could make 100,000 products and you still have to pay that rent. So the rent amount is a fixed cost because that rent amount stays the same no matter what kind of activity happens in that building. So when we're coming up with a cost graph, we're going to have our independent variable here on the horizontal axis. Then we'll have our dependent variable here on the vertical axis. Okay, this is our y-axis, this is our x-axis. So the independent variable is the variable that drives any changes in our dependent variable because the dependent variable depends on the independent variable. So in this case, when we're talking about cost behaviors, our independent variable is our volume. So what we can see here with fixed costs, no matter what the volume is, our costs do not change because the basic rule of fixed costs is that fixed costs are not dependent on volume. So no matter what our volume is, fixed costs are going to stay the same. So in this example here, we've got fixed costs of approximately 32,000. So it doesn't matter if we make 0 units or 2,000 units, our fixed costs are always the same. Now let's talk about variable costs. Variable costs, by definition, are costs that vary in direct proportion to our volume. So in this case, we're told that our variable costs are $20 per unit. So for every single unit we make, the total amount of variable costs is going to increase for each unit. So let's look here. If we make 0 units, our total variable cost is 0 because variable costs are dependent on our independent variable. So if our independent variable is 0, our total variable cost is also going to be 0. On the other hand, let's say our independent variable is 2,000 units. You can see here we have about 40,000 in variable costs, total variable costs, because that's 2,000 units multiplied by $20 per unit for total variable costs of $40,000. So what you can see here, these two lines, this is our total fixed cost line and our total variable cost line. Now, if you'll remember, I mentioned that products usually have 2 types of costs, fixed costs and variable costs. So the total cost of a product is going to be the sum of your variable costs plus your fixed costs. So what you can see here, this top line in green, this is our total cost line. All this is a line that has the same slope as our variable costs because it's still going to increase with the same proportion of our variable costs. But what you can see here is our total cost line, rather than beginning at this origin of 0, our total cost line will begin sloping upwards from the fixed cost line. Because even if our volume is 0, that means that we have 0 in variable costs. But remember, at a volume of 0, we still had those fixed costs of 32,000. So our total cost line here would be made up of total variable costs plus total fixed costs. Or in other words, it would be zero variable costs plus 32,000 in fixed costs. So that's why we're going to start here. But it's basically just going to be a line that has the same slope of the variable cost line, but at every point it's going to be $32,000 greater because that's the amount of the fixed costs. And our total cost line is simply our fixed costs of $32,000 plus whatever our variable costs are at the various volumes. So just a basic understanding of our total costs. So these are costs in total. These are all the costs for all of the units that we made. Now we can talk about our costs on a per unit basis. And this is going to be the opposite of what we saw before. So let's look at how that works. What you can see here, we've got our total cost line again in green. This total cost line again is still going to be the fixed costs per unit plus the variable costs per unit. So there's really not much new here. You're just adding the two together for your total cost line. But the big difference here is that we're talking about costs on a per unit basis. Now, if you'll remember, when we talk about variable costs, we say that variable costs depend on activity. And for this example, we said our variable costs were $20 per unit. So when we're talking about a per unit basis for our understanding of costs, now on a per unit basis, our variable cost line is going to be our horizontal line. Whereas when we talked about costs in total, we had our horizontal line was the fixed costs, and then our variable cost line in total was the one that had the positive slope. Down here, instead of talking about costs in total, we're talking about costs on a per unit basis. So what this tells us is it doesn't matter if we make 0 units, 200 units, or 2,000 units. Each of those units will cost us $20 per unit for our variable costs. So that variable cost per unit dollar amount does not change. That's why this is a variable cost line and it is horizontal. Now let's look at our fixed cost line. Remember, if you're talking about costs on a per unit basis, the way you get something to that per unit cost amount is you take your total fixed cost and divide that by however many units you have made. So, if we make 1 unit, the fixed cost for that 1 unit is going to be calculated for this example as $32,000 in total fixed costs divided by 1 unit. So in that case, the fixed cost per unit would be $32,000. But then what happens if we increase that denominator? Anytime we increase our denominator, it's going to make our per unit amount decrease. So let's say again our total fixed costs are $32,000. What would be our per unit fixed cost if we made, say, 1,000 units? You simply take $32,000, divide that by 1,000, and that tells us that our fixed cost per unit is $32. So at 1,000 units, our fixed cost per unit here is $32. Our variable cost per unit is $20 because it's always $20 per unit. Add 32 plus $20, and that gives us a total cost per unit of $52, 32 plus 20. So you can see here, that's why our total cost line and our fixed cost per unit decline. We have a decline or a negative relationship here because for our fixed costs per unit and our total cost per unit, those are going to decrease as we increase our volume. Why is that? That is because we will be allocating the fixed costs over more units as we increase our volume. So this is very important to get an understanding of what's going on here. Just because you can understand how volume affects your end profit, if you can see how it affects or how our cost setup, do we have more variable or more fixed costs, that has a big impact on how our change in volume affects our profit. So now we're going to look at three different methods that will allow us to measure cost behavior. And what I mean by measuring cost behavior, once we have an understanding of how our costs behave, meaning our fixed and our variable costs, we can analyze that information and we can come up with an equation that helps us to estimate what our total costs will be at any area of quantity for making our product. So let's look at that. As a reminder, this is what we were looking at before. Remember, we've got our total cost line that is made up of our total fixed costs plus our total variable costs. So here is our total cost line. What we can do is we can analyze our different costs for our products. Then we can come up with an equation that represents this total cost line. Once you have the equation that represents this line, you can plug in different volumes or a different number of units or quantity into your total cost equation to estimate what your total costs will be at a certain quantity of units. The reason it's important to estimate your total costs is because anytime a company is trying to budget for the coming year or make decisions about whether or not they're going to sell a product, they need to understand the revenue for that product and they need to understand what that product will cost. So once they can estimate their revenue and their total costs, they can look at what their end profit would be, and then they can determine whether or not it would be a good decision to move forward with making a particular product at a certain volume. So that's all we're doing now is looking at three different methods for coming up with this total cost line. It doesn't matter which method we use. We first have to go ahead and have an understanding of some historic data, and we'll use that historic data to begin to come up with this total cost line. So we're going to look at three methods. We're really going to concentrate on two methods in this class, but I want to go ahead and at least tell you about the third method. So we've got three methods. What we're going to look at in detail in this class is the scatter diagram method, the high-low method, and the least squares regression. We're not going to spend a lot of time on least squares regression because this is a computerized type method. You could use a graphing calculator, you could use Excel to compute least squares regression. But I'll go ahead and tell you that least squares regression is simply a mathematical method of what we're doing in a scatter diagram. And I'll show you how we do that and discuss that when we're going over the scatter diagram. So first we're going to look at a scatter diagram. So to complete cost estimation with a scatter diagram, the first thing we have to do is take our historical data and plot that on our scatter diagram. So at this point, ignore the fact that these two lines are here and even these points of data. The very first step is that we're going to have this blank scatter diagram with our dependent variable, or our total cost, on the vertical axis, and then our independent variable, the units or the quantity, is going to be here on our horizontal axis. So we're going to look at our points of data that we have from our company's history and plot that data onto our scatter diagram. So what I mean by data is we're going to look at various periods of information, look at what our volume was. Let's say here during March, it looks like our volume was about 25,000 units. And what was our total costs? You can see here at 25,000 units in March, we had total costs of also $25,000. So we would plot that point of data here. Then let's look at another month. We don't have the months all labeled here, and the months aren't what's really important. It's these actual points of data. So let's look here, just because this one's right on the line. We had another month that had a volume of 30,000 units, and it looks like they had about 24,000 or so in costs. Then we can move up this way. You can see here, let's say we had about 57,000 units, and what were our costs at about 57,000 units? You can see here, if we come over, it looks like we're at about 26,000 or so in total costs. So that's all we're doing is taking our data and plotting it, putting little plotting points here on our scatter graph. Then what we will do is look at all of our points of data, and we will draw this line to show a line that seems to fit our points of data. You're just using your own human eye, and you're looking at these different points of data and trying to draw a line that you think best fits the relationship of this data. So this is our scatter diagram. If we were using least squares regression, we could use our graphing calculator or Excel. We would do the same thing. We would plot our different points of data, and then we would use least squares regression to plot the correct line. There is not going to be one single perfect line that goes through every point of data, but using least squares regression, you can create or you can plot the line that is the actual best fit. The difference between the two is simply using the human eye versus a calculation of the best line. Because if everyone in this class, including myself, plotted all of our data on the scatter graph and then we all drew our line, all of our lines would probably look similar, but some people's lines may be a little bit higher up or may have a little bit different slope or a little bit lower. But again, we're just getting an understanding of the costs, and these are all based on coming up with an estimate. So it doesn't have to be perfect, but it does begin to give us a good understanding of about what our costs would be at various quantities. So once we have drawn this line, we can come up with an equation that represents this line. The line is typically stated, if you've had any basic math classes, the equation for a line is simply y equals mx plus b. So we'll define what all of those are. You can see here this is the actual equation for our line. So we have y equals mx plus b. So we've changed it here. B represents our fixed costs. So we're just showing our fixed costs we're told are $16,000. So y, or total costs, equals $16,000 plus the mx portion. M is going to be our variable cost per unit. X is going to be the quantity. It's pretty easy to come up with your fixed costs because you can see here that's where that fixed cost line is at about $16,000. Also, we're told exactly what $16,000 is. But how do we get that cost per unit for our variable costs? If you'll remember here, we showed that it's about 20 cents per unit, but how do we come up with that? So to get our variable cost per unit, it just takes a couple simple steps. We pick 2 points of data, and we will calculate the ratio that you see below, which is the change in our cost over the change in units. You pick 2 points of data and calculate those changes. To make things easy, I normally pick one of my points of data as being the origin, because the origin we already know is going to be a volume of 0. And what is the cost at that point? The cost at that point is just our fixed cost, so $16,000. So that one's always pretty easy. Then you can pick another point of data. Here you can see this line that we've drawn here. This happens to be the point of data that we have selected. So we had 40,000 units at this point of data. And then you need to come over here and see approximately what is the total cost. If you come over, you can see at this volume, we had an approximate total cost of about $24,000. So we take $24,000 minus $16,000 because we had a cost of $24,000 at a volume of 40 and a cost of $16,000 when we had a volume of 0. So this is our numerator here. This gives us $8,000 on our numerator divided by the change in our volume, 40,000 minus 0, so you've got 40,000. That tells us that this variable cost is increasing at a slope, and it's approximately increasing by 20 cents per unit. So we can plug that into our equation. So y, or total cost, equals our fixed costs plus our variable costs. So 16,000 plus 0.2 multiplied by x. We can then use this equation to estimate what our total costs will be at any volume of units. We could plug in, say, 100,000 units or 200,000 units by just changing this x, this quantity variable here, and this would give us an estimate of what our total costs would be. So again, the scatter diagram and least squares are fairly similar. We're plotting our points of data. The only difference here is with a scatter diagram, you're using your human eye to come up with the line of best fit, and then again, using your human eye to calculate what your change in costs would be to come up with the variable portion of our costs. We're kind of estimating here as we go. So the scatter diagram is nice because you can do it, you can just plot things on paper and come up with your equation. Least squares regression, on the other hand, is going to be calculated mathematically. So it's going to be the exact line that is the best fit. So it's typically going to be a better estimate, but it also can be more complicated because you have to have more sophisticated materials to do it. Now we're going to look at the high-low method. The high-low method is just another method of coming up with the equation that represents our total cost line. Now, in the least squares method, or with the scatter graph, we are taking into account all of our different points of data to come up with our equation. The high-low method, on the other hand, we are going to pick just 2 points of data and come up with an equation based on those 2 points. So there's a benefit to the high-low method because it's really the most simplistic. We're not having to draw out a graph and plot all of our points of data. We're just selecting 2. So this can be a quick and an easy method. But the downfall is that we're only using 2 of our points of data rather than using all of this data that's relevant and important. So the high-low method, again, the benefit, it's easy, it's quick, but the downfall is, again, we're only using 2 points of data. So first we have to decide which 2 points of data we're going to use. And if you look at the title of this method, it is the high-low method. What that means is we are going to select our 2 points of data based on the highest quantity and the lowest quantity periods. So you can look here, we've got various points of data, and we will select the 2 points of data, or in this case the 2 months, the one that has the highest level of activity and the one that has the lowest level of activity. So you'll go through here and find your high and low months. It looks like here February happens to be our low month, and then let's keep scrolling through, and it looks like here that October is going to be our high month. So we will use this information to calculate our equation. The way we do this is first we will calculate our variable cost per unit, and we do that by looking at the change in total costs based on the change in the level of activity, and we'll look at that as we get to the next slide. Once we know our variable cost per unit, we can then solve for our total fixed costs. So let's look at how this works. Here we have our high and low levels of activity, and what we're doing is very similar to coming up with the slope of the line when we were doing our scatter graph method. We're just using 2 points of data that are defined. Remember, in the scatter graph method, we could pick whatever points of data we wanted, but in this method, we're using the high and low points of data. So what we do is we calculate the change in activity, and that's with the high month, which was October. We made 67,500 units compared to February, where we made 17,500. So we had a change in activity of 50,000 units. The difference in our costs when we changed from the high to low month, we had a total difference in our cost of $8,500. So we'll put the change in our dependent variable in our numerator and the change in our independent variable down here in our denominator. What that tells us is that the change in our cost due to the change in our units is due to our variable costs, because remember, it's only our variable costs that vary in total based on our activity. And when we calculate $8,500 divided by the change in units, that tells us that our variable costs are 17 cents per unit. So let's go back and talk about this. We now have an estimate of what our variable costs are per unit. How do we then calculate our total fixed costs? If you'll remember, total costs are fixed costs plus variable costs. So anytime we have two parts of an equation, we can solve for the third algebraically. So let's talk about what we have now. Remember, total costs equals total fixed costs plus total variable costs. We already have the total cost numbers for both February and October. We were given that information. We do not know what portion of these total costs are variable or fixed, and that's what we need to solve for. But what we do know is what our variable cost per unit is. So if you multiply variable cost per unit by the number of units produced, we can calculate our total variable cost. Once we know our total variable cost, we have two parts of the equation. Remember, total costs equals total fixed costs plus total variable costs. Using our quantity and the variable cost per unit that we just calculated over here, 17 cents, we can then solve for our fixed costs. What you can do is you can choose either the high or the low level of activity or the low month to calculate or solve for our fixed costs. You'll get the same answer no matter what you do, but just for simplicity here, because this is the first one listed, we're going to solve for our total fixed costs using this high month of activity. So our total costs, $29,000, equals the fixed costs plus the variable costs. Okay, variable costs we just solved are 17 cents per unit. Multiply that by the activity of 67,500 units. So now we have total costs is 29,000 equals fixed costs plus total variable costs of $11,475. We then algebraically solve for fixed costs, and we know fixed costs are $17,525. So now we have our equation that fits our total cost line. Total costs equals $17,525 plus 17 cents. If you'll remember from using our scatter diagram method, we had a slightly different total cost line. If you'll remember, it was total costs equals $16,000 plus 20 cents per unit. So you can see the two methods give us a slightly different equation. But the important thing is these are all estimates. We're just trying to estimate what our total costs will be at a particular volume at some point in the future. Now, between the high-low method and the scatter diagram method, remember the scatter diagram used all points of data, whereas the high-low method only uses two. So if I was trying to choose which line or which equation I was going to use, and I had calculated at both methods, I would probably use the scatter diagram method, because that takes into account all points of data, so that line is probably better representative of all of the activity that we've had, or all the points of data. So again, high-low method, it's a great way to be able to estimate your costs and do it very quickly, because we're not using all that time plotting all kinds of points of data and then coming up and drawing our line that we think is the best fit. So there's pros and cons to both. Mostly the high-low method is fairly easy, but it's only using 2 points of data. We've already gone over least squares regression, but least squares regression is simply using Excel or using a graphing calculator, or there is a way you can manually calculate the line of best fit, but it would be very complicated. But it is a mathematical calculation of a line that best fits all of your points of data. So when you're using least squares regression, it's the same idea as the scatter graph, but you're taking out the human variable. So here we just have a summary of the different total fixed costs and variable costs per unit using our three different methods. So you can see here, none of the methods are exactly the same, but each method has its pros and cons. The main con for the high-low method is it's only using 2 points of data. However, it is very simple and quick and easy to use. The scatter diagram and least squares regression Both of these use all points of data, so I think it gives you a more well-rounded picture of how your costs behave. The scatter diagram you can do fairly simplistically using a piece of paper and a pencil. Least squares regression, instead of being able to do it simplistically, you normally need some type of software that can do this for you and can calculate it for you. So it's much more complicated. However, it does have the pro that it takes out having to eyeball what line you think best fits, and it takes out any type of human error. So again, these are all estimates, and none of them are going to be perfect because that's the way estimates work. It just gives us an understanding or an expectation for what our costs would be at different quantities or different levels of activity. Moving forward, we're now going to start calculating and coming up with a break-even analysis. From there, we can expand it to get an understanding of what we call the margin of safety. And again, we can expand the break-even analysis to also calculate your required volume or your required quantity to make a specific profit. So we just make one small adjustment and we can go from a break-even analysis to a specific target profit analysis, and we'll look at all of that. But first we have to define what we call the contribution margin, because we'll use the contribution margin in our break-even analysis. The contribution margin is simply the difference between your sales revenue and your variable costs. And what the contribution margin tells us is it's the portion of your revenue left over to contribute to your profit. Because if you'll remember, sales minus your variable costs and your fixed costs equals profit. So once you calculate your contribution margin, everything left over is first able to cover your fixed costs, and then everything beyond that is profit. So contribution margin, you can look at it on a per unit basis or in total, but on a per unit basis, it would be the sales price per unit minus the variable cost per unit. You can also calculate a contribution margin ratio, which is the contribution margin per unit divided by the sales price per unit. So here we just have an example. If we have a sales price per unit of $100, variable costs of $70, that gives us a contribution margin per unit of $30. So what this is telling us is that anytime we make a sale, the first $70 is always going to go towards covering our variable costs. Because for every unit we sell, we will have $70 of variable costs. So it's this $30 that is left over that's available to contribute to our profit. So there are two ways that this could go. This $30 could be 100% profit, or if we have fixed costs, we will first cover those fixed costs, and then any excess goes to our profit. So we can use this to begin to calculate a break-even point. When we're calculating a break-even point, if you'll remember, I mentioned break-even is the point where a company does not make a profit, but they do not have a loss. So they're breaking even, or they have a profit of 0. We can calculate a break-even point with a very basic break-even calculation. Before we get into this, I just want to explain where this is coming from. Now, you do not have to solve for this break-even formula for this class, but I do want to describe how we're getting to it. This break-even point is simply an algebraic rendition of our overall profit formula. If you remember, profit is calculated as revenue minus total costs. So we can expand that further. Profit is equal to revenue minus fixed costs plus variable costs. So if we're calculating a break-even point, that means we're solving for a point when our profit is 0. So break-even point is derived from that profit formula, and what we're doing is we're putting in all the information that we know. Profit would be 0. We already know what our total fixed costs are. We already know what our variable costs per unit are. We have to be told what our sales information is, or our sales price per unit. And then from there, we can algebraically solve for the quantity. So again, if you're really interested in how all of that works, you can look it up online, how to derive the break-even formula. But that, just so you understand where it's coming from, it is derived from our profit formula when our profit is set at 0. Now that's just a long explanation of where this comes from, but the bottom line is you need to memorize this calculation. So we can calculate the break-even point in two ways. We can calculate the break-even point in units or in dollars. So before we even get into the calculation, what we mean, if we're calculating it in units, this is going to tell us we need to sell 20 units, 40 units, 100 units to break even. Or if we put it in dollars, this tells us we need to sell $100,000 worth of our product in order to break even. So that's what we're calculating here. Alright, so expanding on what we had already begun, a couple slides back, we calculated the contribution margin per unit and then that contribution margin ratio. If you'll remember, we had a contribution margin per unit of $30 or 30%. We're now being told that our fixed costs are $24,000. So what is our break-even point in units? Divide fixed costs by the contribution margin per unit, and this tells us in order to have a profit of 0 or to break even, we need to sell 800 units. If we sell 799 units, we will incur a loss. If we sell 801 units, we will have a profit. So at 800 units, we are breaking even. We have not lost anything. We have not made a profit. We have an ending profit of 0. We broke even. We can also calculate the same thing in dollars rather than units. Fixed costs divided by the contribution margin ratio, so 24,000 divided by 30%, tells us that we need to have 80,000 of monthly sales in order to break even. Now, using this break-even point in dollars is helpful, it's useful, but to tell you the truth, as long as you memorize this formula, you can still come up with the same answer. If you'll remember from a couple slides back, they told us that our sales price per unit is $100. So if we can calculate the break-even point in units, we can easily calculate the break-even point in dollars without even having to use our contribution margin ratio. The way you do that is take our break-even point in units, 800 units, multiply that by $100 per unit, and that'll give us this same answer of $80,000 of monthly sales in order to break even. So the bottom line is you've got to memorize this break-even point formula. Most importantly, the break-even point in units. Because as long as you can get this right, you can solve for the break-even point in dollars. So now let's talk about the margin of safety. The margin of safety is getting an understanding of what do we expect our sales to be. Compare that to what our break-even point is, and the space or the distance between our expected number of sales and what it takes us to break even is the margin of safety. So this example here, we expect to sell $100,000 worth of our product. However, we know that as long as we sell $80,000, we break even, meaning we don't lose money. So the margin of safety is anywhere between our expected sales and our break-even sales. We can calculate the margin of safety as a percentage. That's simply going to be $100,000 minus $80,000, which is a $20,000 margin of safety. Then divide that by the expected sales, and that tells us we have a margin of safety of $20,000 or a 20% margin of safety. What this tells us is we expect to sell $100,000 worth of our product, but we have a margin of safety of 20%, meaning that even if our actual sales fall 15% or 20% below what we expect, we're still safe, meaning we're not losing money. So as long as our sales fall somewhere in between our expected sales or 20% less than our expected sales, we're still going to be within that safety net, meaning we may not make as much money as what we expected, but at least we won't be losing money. Now, if our sales drop 25%, we have then dropped below the margin of safety, and therefore we would be in the loss zone. Now, margin of safety is only talking about if sales decrease. If sales increase beyond the expected sales, we're going to be increasing our profit. So again, margin of safety is talking about the distance between our expected sales and what it takes to break even. So let's look at what we call a cost volume profit chart. All we're doing here is we are going to be plotting our revenue and our cost lines, including our total cost line, to see how different points or different volumes affect our overall profit. So what you can see here, we've got our two different costs lines. We have here our fixed cost line, and then we've got our total cost line. If we wanted, we could also show our total variable costs, and that would just be a line here below the total cost line that starts at the origin rather than up here at the fixed costs. Then what you can see here is we have a sales line. So this is new. We haven't plotted a sales line. All we're doing here is plotting our sales. So for example, if we sell 0 items, we have a revenue of 0. But then let's see if we sell 200 items, we have revenue of 200,000, because again, remember our sales per unit was $100. So here if we sell 800 units, you can see 80,000 in our profit. So we've already calculated the break-even point in sales dollars and in units. So when we plot all of these various lines here, the place where our total cost line and our revenue line, where those intersect, this represents our break-even point, because remember, when we break even, we have a profit of 0. Or in other words, our revenue and our total costs are the same. So anywhere in here that we increase our volume, you can see from the break-even point and beyond, or to the right, our revenue is increasing. So is our costs, but you can see as we increase, we are going to be increasing our profit. So as long as our quantity falls within this area, which is 800 units or $80,000 or more, then we will be earning a profit. If our volume falls below the break-even point, we would be incurring a loss. Now, as we begin to move forward, we're going to be looking at a cost volume profit analysis. And if you'll remember, I mentioned that a CVP analysis is simply taking all of the variables that go into our profit calculation, and if we change one of those variables, how is that going to affect our profit? So profit is made up of a couple basic things. We've got the revenue per unit, the fixed costs, the variable costs per unit, and it takes into account the quantity. So if we change any of those 4 variables, it's going to have an effect on our profit. If you'll remember before, when we first calculated our break-even point, we had fixed costs of $24,000, and we had a contribution margin per unit of $30. Now we've made one simple change. We've said that the company has changed their sales revenue to $105 rather than just $100. And the expectation here is that they can make this adjustment without affecting their quantity or anything else. So now our contribution margin per unit is $5 higher, because it's $105 minus $70 of our variable costs. So what happens to our break-even point? 24,000 divided by now a larger denominator makes our break-even point go down, meaning that now rather than having to sell 800 units to break even, when we have raised our sales revenue per unit, we have therefore made our break-even point decline because we have a higher contribution margin. So that's basically what we're going to be doing with a CVP analysis. We're going to be changing some of our different variables to see what happens with our profit. So one thing we can do with a CVP analysis is, rather than simply calculating the break-even point, we can make a small adjustment to our break-even formula to allow us to calculate how many units or what our sales dollars have to be to make a particular profit. So if you'll remember, the break-even formula is simply a formula that we derive from our profit calculation. So when our profit is to be a break-even profit, that means our profit is 0. What we can do is make an adjustment, and instead of calculating for a profit of 0, we'll put in our target profit. We can then again change the formula around and derive our new break-even formula, or now our target profit formula. So the bottom line is all we're doing is adding that target profit to our numerator. If you'll remember before, the break-even formula was our fixed costs divided by our contribution margin per unit, or the contribution margin ratio. That was at a break-even point of 0. So basically, we could have not changed this formula, and we were saying our fixed costs plus our target income, which at break-even, target income was 0. So we were simply simplifying things and leaving this part out, and then dividing by our contribution margin ratio. But now that we want to solve for our specific target income, we now need to include this in our formula. So fixed costs plus our target income is now our numerator, and then divide that by either our contribution margin ratio or our contribution margin per unit. So now what we're doing is we're saying we want a target income of $12,000, whereas before we calculated that break-even point at a break-even point or a profit of 0, so we didn't have anything extra in our numerator. If we are increasing our numerator but not changing our denominator, what we're going to see is we're going to see an increase in our required sales in dollars or in units, because our numerator is increasing, and that makes sense. If we want to earn a profit versus break even, we need to sell more. So $24,000 was our fixed costs, plus that target income of $12,000, divide that by 30%, and that tells us that in order to make a profit of $12,000, we need to sell $120,000 of our product. We can also calculate this in terms of units. So fixed costs plus the target income, no change here in our numerator. Divide that by the contribution margin per unit rather than the contribution margin ratio, and you can see what has happened. We have to sell 1,200 units in order to break even. If you'll remember, and you have to remember a couple examples back, when we were originally calculating our break-even point in units, it was just fixed costs, or $24,000, divided by our contribution margin per unit, or $30 per unit. That gave us a break-even point of 800 units. So can you see how this makes sense? In order to break even, or have a profit of 0, we have to sell 800 units. But anything beyond that break-even point is going to result in a profit. So we would expect, in order to have any type of profit, we would need to sell more than 800 units. And as it turns out, we need to sell 1,200 units in order to make this required profit of $12,000. So this is just looking at how different changes can affect our bottom line or affect our profit. So what we're looking at is a sensitivity analysis. We're looking at how sensitive is our profit to various changes. All we're doing is calculating our break-even point, or if we have a specific target profit, we'd have that profit up here in our numerator, and we're changing variables that we're interested to see if we change our fixed costs, or if we change something within our contribution margin, how does that affect our end result? So you can see here, now we've changed things up a little bit, and we are trying to calculate our break-even point if we've changed our fixed costs. How have we changed our fixed costs? We've said that our fixed costs have increased. If you'll remember before, fixed costs were $24,000. Well, now we've increased those to $30,000. We've also changed, in this case, our denominator. If you'll remember before, our contribution margin ratio was 30%. Now we have increased our contribution margin ratio, meaning that we're keeping more of our revenue. So it's a 40% contribution margin ratio. What that tells us is that in order to break even with these new changes in our parameters, we need to have sales of $75,000. Using our understanding of the break-even point, we can now adjust it to be able to compute the break-even point for a company with multiple products. In the real world, we know most companies do have multiple products, but to be able to understand the principles of break-even point, you first have to be able to calculate it for a company with one product, and then we can expand our understanding. So what we're going to do here is we're going to be still calculating break-even point, but first we have to come up with our composite unit. What that is we're basically going to look at the sales mix of our company. So how much do we sell of product A versus product B, and use that information combined with the contribution margin for each unit to come up with what we call a composite unit. So all we're going to be doing is using the break-even point formula and changing it a little bit to calculate the break-even point in composite units. We can then use the break-even point in composite units, multiply that by our relative sales mix to come up with our sales for each specific product. And we'll look at that and make it more concrete as we move forward. So here all we're doing, we'll take our fixed costs, divide that by the contribution margin per composite unit. And that gives us our break-even point in composite units. But first let's go ahead and calculate the composite unit. We have an example here. We have a company that offers 3 products. You can see them shown here. Most importantly, we have the unit contribution margin for each product, and then we have the sales mix ratio. What this means, for every 1 budget haircut, we have 4 basic haircuts. And again, for every 1 budget haircut, we're going to see about 2 of the ultra services. So we'll use this information along with the contribution margin information to come up with our composite unit. So first let's look at our sales price, and then we'll use the variable cost. You have here the sales price per unit. Multiply this by the sales mix ratio. Again, it was 4:1. So this is the total sales price relative to each other. So again, for every 1 budget cuts are at $16. So every time we bring in $16 for a budget cut, we'll be bringing in $20 for 4 basic cuts, or in other words, $80. Do the same thing, we'd be bringing in 2 ultra cuts for $64. So our total selling price for a composite unit would be $160, which is just the sum of these. We'll do the same thing here with their variable costs, $13, $18, and $8. Multiply that by the sales mix ratio. So then we have the selling price, multiply or add that together, and we have a total variable cost per composite unit of $96. All we do now is calculate our contribution margin. So let's go back a slide. Remember, our sales price per composite unit is $160. So we take our sales price minus our variable cost per composite unit. So $160 minus 96 gives us a contribution margin per composite unit of $64. We'll then use that in our break-even analysis. We were told we had $192,000 in fixed costs. Divide that by $64 of our contribution margin per composite unit, and that tells us we need to sell 3,000 composite units. So this doesn't mean we just need to sell 3,000 total units. This is composite units. We then need to multiply this by our sales mix to see the exact sales per specific service. So again, we use that 4:1. So basic is going to be 4 multiplied by 3,000. So we'll need 12,000 of the break-even, 12,000 of the basic. Ultra, 2 multiplied by 3,000. 6,000 of the ultra cuts. And then the budget cuts, those were 1, so that'll just stay at 3,000. So this tells us in order to break even, we need to have a total of 21,000 haircuts. And this is the breakout of how they will be. 12,000 of the basic, 6,000 of the ultra, $3,000 of the budget. This is just proof of the fact that we will break even at this point, just showing our various revenue at each of these different volumes, our variable costs at these volumes, and you can see here that we would end up breaking even, meaning that our revenue minus our variable costs minus these fixed costs is going to leave us at our break-even point, or a net income of 0. Finally, we're going to look at what we call the degree of operating leverage. We spent a lot of time talking about variable costs, fixed costs, and contribution margin. When we talk about operating leverage, we're getting an understanding of how a company is set up. Do they have more fixed costs, or do they have more variable costs? And when we talk about operating leverage, we're also looking at the degree of risk that a company has. Now, if you've ever taken any type of finance classes, you'll understand that any time you take a risk, you also have the opportunity for a higher return. On the other hand, if you take a risk, you could lose more. So that's what we're talking about when we're talking about operating leverage. I'll go ahead and tell you that a company with more fixed costs as opposed to variable costs is considered more risky, and we say that they have a higher degree of operating leverage. They are highly leveraged. The more fixed costs you have, the more risky you are, and therefore the more leveraged you are. So let's talk about why that is. If you are a company, and we're going to make this very simplistic, we're going to say that you are a company with two scenarios. You either have 100% variable costs, or 100% of your costs are fixed costs. So how do things work out? If you are a company that has 100% variable costs and you make 0 sales, you have $0 in sales, so what are your costs? If your costs are variable, 0 quantity, because 0 sales multiplied by your variable costs is going to equal 0. So you would break even. However, let's say that you do make some sales. Let's say that your variable costs are $5 per unit and your sales are $10 per unit. If you sell 100 units, you are going to have $1,000 of revenue, and then 100 units multiplied by $50 for your variable costs, you're going to have $500 in variable costs. So you make a profit of $500. Let's talk about if you have fixed costs. Let's say all of your costs are fixed costs and you have costs of $200. Let's just make it easy. If you make sales of 0, what happens? You still have fixed costs, therefore you have a loss. So you have a full loss of the full amount of $200. But what happens if you make sales? Again, let's keep things the same. Let's say we sell 100 units. In each of those units, we get $100 for it. $100 multiplied by 100 units, we have $1,000 in sales. What about our costs? Our costs are fixed. They don't change. So we still have $200 of costs. Revenue of $1,000 minus $200 of costs gives us an ending profit of $800. So can you see that if we have all variable costs, our costs are going to increase right along with our revenue proportionately. So every time we make a little more money, we're also going to spend a little bit more money because those variable costs are going to increase right along with our quantity. On the other hand, if we have fixed costs, it doesn't matter what we sell. Those fixed costs are always going to be there. So if sales are bad, it can be really bad because you always have fixed costs, so you're more likely to incur a loss. But in times when sales are good, your profit can be really good because your fixed costs do not increase in proportion to that change in your sales. So let's look at how this happens. The degree of operating leverage is a measure of the extent to which fixed costs are being used in an organization. So the degree of operating leverage is something we can use to calculate if we have a specific change in our sales or our revenue, what's going to be the end effect on our profits. So now that you understand why we have this effect when we have fixed costs, you can now better understand this operating leverage calculation. So a company that is highly leveraged is a company that has more fixed costs as compared to their proportion of variable costs. So anytime we see an increase in this degree of operating leverage, this means that a company is more highly leveraged. Therefore, anytime they have a change in revenue, their change in profit is going to be larger. So the larger this number, the larger we are going to see the profit vary. And this could be negative or positive depending on which way our sales move. Here's how we calculate the degree of operating leverage. It's our total contribution margin in dollars divided by the pre-tax income. So, for example, if we had total contribution margin in dollars of $36,000, divide that by a pre-tax income of $12,000, this gives us a degree of operating leverage of 3. So anytime we have a percent change in our sales, we will multiply that percent change in sales by 3 to see what it's going to do to our bottom line or to our profit. So if sales increase 10%, 10 multiplied by 3, we'll see a 30% increase in our income. If sales decrease by 10%, we will see 10 multiplied by 3, or 30% decrease in our income. So the bigger this number, the bigger the multiplier, and therefore the more of a variance you're going to see. So here we just have the proof of how the degree of operating leverage estimates the change in our income. So you can see here, when we have a degree of operating leverage of 3, we'll expect to see any change in our income to be 3 times whatever change we saw in our sales. So for example, a 10% increase in our sales would give us sales of $132,000, because 10% of $120 is $12,000. So $12,000 plus $120,000 gives us $132,000 in sales. If we went and calculated our full income statement, if we had sales of $132,000, we would see that our pre-tax income would be 30% more than $12,000, or we would end up having pre-tax income of $15,600. So again, the larger our degree of operating leverage, the larger effect we're going to be seeing on our income. So this could be a good thing in years when we're seeing an increase in our sales, but it's going to be a bad thing in years where we see decreases in our sales, because we're going to see a larger decrease in our income as opposed to that decrease that we're seeing in our sales number. So the degree of operating leverage just gives us an understanding of the variance that we're going to see in that income number. Again, if a company is highly leveraged, they're considered to be more risky. Risk in the world of finance can be a good thing, because if you're willing to risk, you could also make more. On the other hand, a company that is not highly leveraged, they're going to be more predictable, meaning they're not going to have such a large variance. So, for example, one company that has a degree of operating leverage of 3, a company that has a degree of operating leverage of, say, 1, would have a much lower variance, meaning that for every 10% increase in their sales, they're only going to see a 10% increase in their income, or vice versa. If they see a 10% decline in sales, they're only going to see a 10% decline in their income, as opposed to the more highly leveraged company who saw a 30% decline. So it all depends on what you're looking at for an investment or what you want for your company. Are you willing to risk in hopes of a greater return, or do you want a company that's a little bit more stable, more slow growing, and more predictable?